Monday. All right, here's the 6-3 stuff we talked about the other day. Not a big deal. Not a big deal. Just this sums it up pretty well right here. Just looking at some patterns of some multiplication patterns. Okay, some ways that we can, instead of having to FOIL this stuff out, we can just follow just 2 or 3 or 4 little patterns we'll remember. Later on, we'll deal with how to expand even bigger powers of binomials. I'll give you a formula for that. But for now, we're just going to limit it to up through cubics. So what do we do with these? What's this top one equal to? If we take the product of 2 conjugates like this, what do we get back?
A squared minus b squared.
Good. Okay, a squared minus b squared. And that's just the reverse of that factoring pattern that we looked at in chapter 5. Difference of 2 squares factors into the conjugates, right? Okay, what about a plus b quantity squared?
A squared plus 2ab plus b squared.
Good. A squared plus 2ab plus b squared. And some ways you can sort of remember this. Now, don't think this is a pattern, because this won't always be this way. But notice that the 2's match up. Okay. And then look at the way the patterns the powers behave with the a's and the b's. We'll see this behavior in all of these. Every time we expand a binomial like this, a plus b to any power, notice that the exponents always add up to 2 in this case, right? Whatever the power of the binomial is, they always add up to that power. There's an invisible b to the 0 there that we just don't write, right? What is anything to the 0? 1. So it's there, but we just don't write it. And then there's an invisible a to the 0 right there, right? And so 2 plus 0, 1 plus 1, 0 plus 2. The exponents always add up to that power, right? Okay, what about a plus b cubed? Okay, yeah, so a cubed, b to the 0, which we wouldn't write.
3
A squared, b to the 1, good. Plus
b cubed.
a to the 1, b squared. Good, a to the 0 we wouldn't write. B cubed. And notice the symmetry, right? If we split these things down the middle, notice that the coefficients are symmetrical about that midline. I've got 2 3's and 2 1's if I just look at the coefficients, right? There's a 1 there, 3 there, 3 there, and 1 there. Symmetrical. Same thing up here. If I split this down the midline, well, it splits right on the 2, and then there's a 1 on either side. So there's a symmetry about it like that always. Okay? Okay, so then what do we get? Let's take an example. Specific example here. So what if I want to expand out 2x minus 3 cubed? What is a equal to then? 2x. Okay, so a is like a 2x. What's b? Negative 3. And then we're just going to follow that pattern, right? Okay, so we've got a cubed, so that's the quantity 2x cubed plus 3 times a, which is the quantity 2x squared, times b, negative 3, plus 3 times the quantity 2x to the 1 times negative 3 squared, plus negative 3 cubed. Make sense? We're just plugging in those values, and if we simplify that, what do we get? Well, what is the quantity 2x cubed? Okay, good. 8x cubed, isn't it? I have to distribute the power to both of the factors. So you get 2 cubed times x cubed. So this one is 8x cubed. Now, what about this next term? The 2,
36x squared.
the 2x quantity squared is really going to be a 4x squared, isn't it?
12x squared, sorry. 12x squared.
12? I've got 3.
Oh, sorry, that's another negative. Negative 36. Oh, what did negative 9 times square. So it's negative 36.
Okay, so yeah, so I'm going to get 3 times 2 is 6. Oh, so 3 times 4 is 12, sorry. Times negative 3.
Negative 36x squared.
Okay, good. So the number part is negative 36, and then we get an x squared. What about the next term? Let's see, we're going to get negative 3 squared is
Should be the same.
9. Okay, so 3 times 2 times 9. 6 times 9? 54. And then that's just going to be x, right? And then finally, negative 3 cubed?
9.
Negative 27. There it is. Okay? Make sense? Okay, and after you do a few of those, they get a lot easier. All right, so that's 6-3. That's really all you're doing in 6-3. It's just those expansion patterns. No big deal. Yeah, I want to take a look. Moving into 6-4. 6-4 is a pretty big section. I want to take it in a couple pieces. To put it in context, I want to just kind of remind you about some things you already know, but we haven't maybe thought about specifically in a while. What do we do if we've got something like this? How would I solve that equation?
Quadratic formula.
Quadratic formula. Sure, why not? Right? Quadratic formula. Maybe it would factor. This one actually would factor, but if we've got a number in front of x squared and we can't divide both sides by something to trim it down, right? Then we would just use quadratic formula. That's really nice. It's in hindsight, what you're going to see is that even though Chapter 5 might have seemed kind of tough when you were doing it, you will be amazed how easy it is upon reflection. I mean, it's somehow it just happens. You just kind of absorb it, and before you know it, you're just really good at that stuff. It's no big deal. We just use quadratic formula. Quadratics are not a big deal. When we want to solve quadratic equations, we have quite an arsenal. We can always use quadratic formula. If it's easy to factor, we can. We can also, how would we do one like this? What if we had how would I do that one? Okay, what do you mean by that? You're right. How do we usually describe that? Okay, good. Yeah, if we can point to a single x, so we could isolate it, right? We could just push everything to the other side. What would be the steps we go through in order?
Divided by 2.
Okay, subtract 4.
Divide by 2.
Divide by 2. Square root. And then add 3, and we get the x by itself. And then the only tricky part, you got to remember there, when I square root both sides, what do I have to include? Plus or minus, yeah. So not that big a deal. We were able to solve quadratic equations pretty easily. What about this, though? What happens when we run into something like this? What if we have, say, what about that one? We don't know yet, do we? That's 6-4. How do we deal with factoring polynomials? Or how do we deal with solving polynomial equations like this that are bigger than quadratics? The short answer is very carefully, because they don't always work. We can't always do it. But sometimes we can. Unfortunately, these are a little bit harder because there is no silver bullet. There is no cubic formula like there's a quadratic formula. We have one for quadratics, but when we get to cubics, we're sort of stuck. We just have to either be able to factor that or we don't know. Now, there are some techniques that are pretty tedious and time-consuming that sometimes work and sometimes don't, but you know, we're not going to focus on those a lot because if it's a really hard polynomial to solve, like this one isn't, but some of them are, some of them won't factor easily, then we'll probably just use our graphing calculator and either graph the function and look for the zeros. You know, there's some tricks we can do with the graphing utility that make this pretty easy. But we do want to know how to deal with the group of polynomial equations that are easy to solve. Okay. So how do we go about that? Well, you know, just like we did with quadratics, remember when we started off talking about solving quadratic equations, we used examples like this. Before we knew about the quadratic formula, we said, okay, if we could break this thing up into smaller pieces, then we could use the zero product property, and we'd know that each of the smaller pieces, the factors, that the product of the factors would equal 0 when the individual factors were 0. Because the only way you can get 0 for an answer when you're multiplying things together is if one of the things you're multiplying is 0. Right? It could be this one or it could be this one. Well, this would factor into what? What are the magic numbers that multiply to -12 and add to -1?
Oh. 3 and 4.
What are the signs? -4, +3. So if I'm able to break this quadratic expression apart into a product of two small linear factors like that, well then it's not such a big deal. I can say, okay, this product equals 0 either when the first factor equals 0 or when the second factor equals 0. And I know I'm just reminding you, you know how to do this. So our answers end up being either x equals 4 or x equals -3. So factoring is always a good idea, and that always works when we're solving equations. Later on in your math careers, you'll learn to factor other things too, trig equations and exponential equations and all kinds of other weird animals that we won't get to this year, but eventually you will. Okay, so let's take a look then at, skip through this stuff, come back to this too. Let's take a quick survey of the kinds of problems that we're going to take a look at here. Factoring polynomial expressions. They fall into, there's some nice easy ways to approach this. If you organize your thinking about this, I'll help you do that. This section isn't really all that bad. There are a couple of different strategies. In fact, there are three different big strategies we'll use in this section. And they're easy to separate because they depend on the number of terms in the polynomial you're factoring. First, let's take the easiest one. What if we're dealing with polynomials, cubic polynomials that have two terms that fit either of these two examples, either a sum of cubes or a difference of cubes, fit those factoring patterns? What we know is that whenever I see something like this, a sum of two cubes, something cubed plus something cubed, call the first something A and the second something B. It will always, every time, factor into this pattern. It's going to factor into the pattern the quantity A plus B times the quantity A squared minus AB plus B squared. Okay, and then if I were to substitute a negative B into this one, every place I had a B, if I substituted a negative B, I would get the other factoring pattern, difference of cubes. A cubed minus B cubed always factors into A minus B times A squared plus AB plus B squared. And we'll look at those in more detail here in a second. But we could take examples like this then. What if I had x cubed plus 8, for example? Now I ask myself the question, whenever I see two terms added together like that, does it fit this pattern? Can I write it this way? Well, I can. X cubed plus 8 cubed could be written as, whoops, x cubed plus 8, sorry, could be written as x cubed plus 2 cubed, right? So I can write it as a sum of two things being cubed. And then all I have to do is follow that pattern. Okay. Well, let's remind ourselves about the pattern again. The pattern was a cubed plus b cubed equals small factor times a big factor. 2 terms, 3 terms. Do you remember what they were? An easy way to remember how this goes. First one was, remember? It was a plus b. So whatever sign that is, goes there. And then the next one has 3 terms, and the powers are always going to add to 2. So I have an a squared term, an ab term, and a b squared term. 2 plus 0, 1 plus 1, 0 plus 2, they all add to 2. And then look what happens. The signs, whichever sign they start with, the next one is going to be its opposite. And then the third one is always plus. That one's always the same. Okay. And the reason I'm talking about these trends, is because if we want to factor a difference of cubes, watch how they compare. AB, a squared, AB, b squared. But the signs, just the first 2 signs, just alternate, and the last sign is the same. Okay, notice that whichever one shows up in the original expression, that's the sign between a and b in the first factor, and then the next one is going to be its opposite. Okay, so that's an easy way to remember how those patterns go. So what is this example going to become then up here? In this case, it's the expression. Well, it's the sum of cubes pattern. Instead of an a, we have an x. Instead of a b, we have a 2. So then we just follow the pattern. So this must equal a, which is x, plus b, which is 2, times a squared, which would be x squared, minus x times 2, which we would write as 2x, right? Plus 2 squared, which is 4. Done. Okay. Now, you might ask the question, if you thought about this a little bit, this quadratic factor that we get, can I go further with it? Does it factor? And the answer is an emphatic no. It's always an unfactorable quadratic when we use this pattern. You'll never even have to try. This is one that will not factor. It's one whose in fact it's going to be a quadratic factor with no real zeros always. Okay. If we were to set this equal to 0 and solve, we would only get i's every time coming out of this part. Okay, so we're done factoring. As soon as we apply the pattern, we're done. All right, let's look at another example. Oh, you know what? Actually, let's do that. The one that was up there. It's a good example. Let's do difference of cubes. Let's try this. Let's take a closer look at this one. 8x cubed minus 1. Okay, the question is, can we write this as a difference of cubes? Can we write it as something cubed minus something cubed?
No. Yeah.
Well, 1 is the same thing as what cubed?
1.
1. Yeah, 1 cubed. Now, what about this first one? 8x cubed. There's 2 parts to it. Well, the x is pretty obvious, right? 2. Yeah, the cube root of 8 is 2. So it's the quantity 2x cubed. So that's like our a, isn't it? Now remind me real quick, what is the pattern? See if you can remember. A cubed minus b cubed is a minus b. Good. Plus. Good. And then always plus. Good. Plus b squared. Good. Okay. So we have to just follow that pattern, right? So a minus b is just going to be 2x minus 1. Now we got to be a little bit careful here with this one. What's a squared going to be if a is 2x? It's the quantity 2x squared. So if it's the quantity 2x squared, I've got to distribute, I've got to square out both the 2 and the x, right? Does that make sense? So this one is going to become what? 4x squared. Good. And then plus AB, so 2x times 1. Right? And then finally plus 1 squared. It's just 1. Done. Okay? No big deal. Following those patterns really isn't that big a deal. There's only 2 of them to know. And probably the hardest part is this first step, really, is just realizing, okay, can it be written as the sum of cubes or a difference of cubes? And we could add to that, by the way, there's one other pattern from chapter 5. Now would be a good time to remind ourselves about it. What is a difference of squares? What does that factor into? We just talked about it in reverse. Difference of squares factors into what? Just did this one in reverse. In fact, there it is right there, right? Remember, if we just go this direction, that's the one that factors into the conjugate pattern. A plus B, A minus B. And what about a sum of squares? Does that factor?
Yeah.
No. That's one that never factors. You're done. If something looks like it would be a sum of squares, it won't factor. So you leave it. So what would this one be then? Which pattern would that follow? Sum of 2 cubes. Good. X cubed plus what cubed? 3 cubed. Okay, good. X cubed plus 3 cubed. Then we'll just follow our pattern. A plus B times A squared minus AB plus B squared. Okay, now what about this guy? That doesn't look like any of them at first, does it? 16u to the 5th minus 250 u squared.
No.
That doesn't look like any of those patterns. But what do we always want to try to do first when we're factoring? Simplify, yeah, but in what sense? We always want to try to. Well, there's no equation here for us to. But we can't do anything with an equation. But we always want to see if we can pull out a greatest common factor. Always. It's always going to make things easier. So what about the number part? Well, let's see. What's a number that goes into both 16 and 250? 2, wouldn't it? Because they're both even numbers. And then what's the biggest power of u that we could pull away from each, divide away from each? U squared. Sure. Okay, so we could factor out a 2u squared. Right, if I divide away, if I undistribute a 2u squared, well, 2 times what is 16? 2 times 8. U squared times what is u to the 5th? U cubed, right? And then when I pull the 2u squared away from the second term, I'm just left with a minus 125. Okay, now let's focus on that part. Okay, the first part's done. We got a monomial factor, single term, that factored out. What about the other part that's left, the 8u cubed minus 125? Can that be, how many terms are in that factor? 2. So maybe it'll fit one of those factoring patterns that involve 2 terms. Which one could it fit, possibly? 8u cubed minus 125. What's the only pattern that would make sense to apply here? Difference of cubes, good. Could 8u cubed be written as one thing cubed? 2u, good. And then 125 is what cubed? 5 cubed. Uh-huh. Good. Okay, so we break it down that way, and now we just follow that pattern. Okay, and that's it. So, okay. All right, so there's the first strategy. No big deal. That's the strategy that we can use for big polynomials with 2 terms. That's an easy one. Okay, what about big polynomials that have 4 terms? We're going to look at one with 4 terms here. Now, this is the one where I cheated a little bit. I showed you guys last chapter. I had you guys do when you factored your quadratic trinomials with a bigger than 1. I showed you a technique for that we called factoring by grouping, which is exactly what we're going to do here. These are actually easier problems because they're already separated into 4 terms. You don't have to do the a times c split b part. You can just, if they factor, they'll factor using the same technique we used for the second half of all those problems. Okay, so I'm going to skip through their explanations. I think it's just a little bit confusing, but let's take a look at this example. You will find that you already know this. Okay, factoring by grouping. Now remember how we did that. When we had 4 terms like this, we broke it into 2 groups, right? We said we got the first group, plus the second group, right? Okay, you'd be absolutely insane not to be watching this right now, because this is a place where you could easily, if you don't get this now, you're going to get behind a little bit. Okay, so what do we do from here? Remember, going back to chapter 5? Greatest common factor. Good. We're going to try to pull the greatest common factor out of the first group, and then that'll leave us with what we call the leftover factor, right? And so we might show that schematically like this. We're going to get some greatest common factor, and then some leftover factor. And then remember that over here in the second group, we're going to do the same thing, but that those 2 have to be equal for this to work. If they're not equal, we're done. It doesn't work. This technique falls apart and we can't factor it. These 2 must be the same. Okay? So let's see if we can do that. What's the greatest common factor from the first group?
1.
X squared. Right? The number part is 1. The variable part would be an x squared. Now if I undistribute an x squared, what am I left with? X squared times what is x cubed? Minus 2. Okay, so we know. Now you've got to watch this very. I'm not kidding. If you're not following this, I don't have that much sympathy, because here's where I'm going to get a lot of questions. I'm tempted to just not answer a question from somebody that's not paying attention. In fact, I really might do that. X minus 2, then, that has to go here if it's going to work. So what you really want to do here, people have a tendency then to want to go, okay, let's start with the second one and factor that. No, don't. Make it easy. You know that this has to go there for it to work. And then the question just becomes, okay, can I undistribute something? Can I factor out something to make that happen? Is there a number that would go here that would work? What would it be? -9. And we can check it. -9 times x is -9x. -9 times -2 is, that's supposed to be an 18. Whoops. is positive 18. Sorry, that makes a little difference, doesn't it? See, I forgot the one. Okay, so it worked. And then all we have to do now is just rewrite our answer in the correct form. So we end up with, let's see, if I pull out from each of the two terms, if I pull out the x minus 2, we're left with x minus 2 times what? What's left over when I take those away from each term?
X squared minus 9.
X squared minus 9. Okay, so there we go. But now, this one's done. We know that one's done because the x is to the first power. It's done. What about this second one? I've got an x squared in there.
It would be x minus 3.
Okay, what does that factor into?
X minus 3.
No. X plus 3 times. Quick reminder. Here's our pattern right there, right? Difference of squares. That's the same as x squared minus 3 squared, isn't it? Right? So this one breaks down into x plus 3 times x minus 3. And so there's our fully factored polynomial. Okay? Product of those three factors. How about that? Okay? So there's an example. Now that's a lot of stuff if you look back at that, but you already knew more than half of that, right? So it should look at least pretty familiar. You got to do a couple, probably to get back on track with these. But if you, going through chapter 5, you've done this already. Okay? And then the last example, this is the last kind. There's 2 of the 3. Here's the third kind. And obviously we need to spend more time on this, and we will. I just want to expose you to them today. Okay, this is going to be, I mean, it's not terrible either because it also relies on stuff we did in chapter 5. This is what we call factoring a polynomial that's in quadratic form. So in other words, can we write it in a form where it looks like a quadratic instead of something bigger? These could be in either 2 terms or 3 terms, and we'll look at one of each. Let's take this example. Okay, now. What about this? Now that looks, what degree polynomial is that? 4th degree, right? 4th polynomial. So it's not quadratic, but can we make it look quadratic? There's 2 terms here. Notice that this x is being taken to the 4th, right? Could I write this, if I wanted to write this as something squared with 2 terms in it, there's only one factoring pattern that's quadratic that has 2 terms. Remember, we said that there is no sum of 2 squares pattern. That one doesn't exist, but there is a difference of squares pattern. So could we write this as a difference of squares? Could we write this as something squared minus something squared?
Yeah.
Okay, the first one, what squared is 81? Well, 9. And then what squared is x to the 4th? X squared, right? Because when I take a power to a power, I multiply the exponents, right? Right? Did everybody see that? Okay, and then 16 is what squared? 4. So that's going to follow our difference of squares factoring pattern, right? So I know this is going to break down into, if that's A and that's B, I'm just going to get A plus B times A minus B, right? So I'm going to get a 9x squared plus 4 times an A, which is 9x squared minus 4. Okay, now we got to look at that step and see, well, can we go further? Yeah. What about this term? Now that looks like a sum of 2 squares, doesn't it? So can we go further? No. We're done. This one is done because it's a sum of 2 squares. Let's make a note of that. So this guy he's done. What about this one? Now that one, it's got a minus sign in the middle, and so that's the one that it maybe could be rewritten to look like a difference of squares. Is there something, can I rewrite 9x squared as something squared?
3x squared.
3x, okay, and then 4 is
2.
Okay. Right? And so that guy's going to break down a little bit further. This one's going to break down into that conjugate pattern. A plus B times A minus B, right? And then we've got this other factor tacked on out front that was already done clear back up here. So we got it. That's our answer. Okay. And the trick was, we were just able to see this thing. If we go back up to the start, we were able to see this thing in terms of a difference of squares. Okay. So that actually is a quadratic pattern. So we made it look like a quadratic even though it was bigger. What about something like this? So what about that one? And this is a good place for us to stop. We won't be able to finish this, but let's see if we can at least get it set up so we can kind of see what's going on.
Oh, wow.
Looks ugly, right? Okay, what do we always want to do first?
Simplify it.
Okay, good. Greatest common factor. Let's see. What's the biggest number that divides into all those?
24.
4. So we can pull out a 4. And then what power of x? X squared. Good. Leaving us with 4x squared times what is 4x to the 6th? 2. X to the 4th. Good. Because when we multiply like bases, we add the exponents. Middle term, I'm going to get what? 5x squared plus 6. Okay. So this guy's done. The question is, what about this guy? Now here's where we'll leave off. But do you see that that's got 3 terms in it? It looks like a trinomial. Now we're used to seeing things like this. We're used to seeing things like, back in chapter 5, this might have looked instead like maybe u squared minus 5u plus 6, where u's are variable instead of x this time. I just want to show that they're different. Right? Now, that still works. What if we think of that u as being an x squared? Right? Because x squared squared is x to the 4th. Right?
So when you use 5 squared?
5u would be the same as 5x squared. Now this factors. If we think of this in terms of packets of x squared, which we might call u, it factors just like it did in chapter 5. What are our magic numbers that multiply to positive 6?
6 and 1.
No, multiply to positive 6 and add to negative 5. So they both must be what sign?
Negative. So
Negative.
Negative 3 and 2.
Okay, so this could look like u minus 3 and u minus 2. But the u is really just an x squared, isn't it? Right? Because what I've really done here is I've taken this x to the 4th and I've thought of it as x squared squared. Right? So those are really u's. I don't have to write it out as a u, but I can just see that I'm looking at this trinomial. Instead of in packets of just x, I'm looking at it in packets of x squared. Right? And then I can rewrite this guy as x squared minus 3, x squared minus 2, and 4x squared, and we got it. And I couldn't really go any further, could I? Neither of those could be written as different squares. Yes, Brandon. Say that one more time.
Don't worry, it'll be fine. Remember, most of them are multiple.
Divided by X. Okay, oh, you start with it. Good.
I mean, we're starting a new chapter.